Hello dear students, welcome to lecture 14 of Security of Information Systems. Today's lecture will be a special one. We will see the top 10 threats to the developers in the security area from Owasp Foundation, and then we will see the injection attacks with details. So who is Owasp Foundation?
Who is the Owasp Foundation? The Open Web Application Security Project (OWASP) is a non-profit foundation that works to improve the security of software. Through community-led open-source software projects, hundreds of local chapters worldwide, tens of thousands of members, and leading educational and training conferences, the OWASP Foundation is the source for developers and technologists to secure the web.
Okay, so let's start with the top 10 of Owasp Foundation. Top 10 threats.
The OWASP Top 10 is a standard awareness document for developers and web application security. It represents a broad consensus about the most critical security risks to web applications.
Okay, so I think you have heard that Thunder.
Companies should adopt this document and start the process of ensuring that their web applications minimize these risks. Using the OWASP Top 10 is perhaps the most effective first step towards changing the software development culture within your organization into one that produces more secure code.
Okay, so what are the top 10 web application security risks?
Top 10 web application security risks.
Okay, I will take a pause to open our electricity. It is just went off. Okay, so the first one is injection. What is injection? We will see that.
Injection flaws, such as SQL, NoSQL, OS, and LDAP injection, occur when untrusted data is sent to an interpreter as part of a command or query. The attacker's hostile data can trick the interpreter into executing unintended commands or accessing data without proper authorization.
Okay, let's see the details of an injection attacks. Alright, so looks like they have prepared a PDF, a table.
Threat agents, attack vectors.
Okay, application specific exploitability 3.
Exploitability, 3. Almost any source of data can be an injection vector, environment variables, parameters, external and internal web services, and all types of users. Injection flaws occur when an attacker can send hostile data to an interpreter.
Security weakness, prevalence 2, detectability 3.
Injection flaws are very prevalent, particularly in legacy code. Injection vulnerabilities are often found in SQL, LDAP, XPath, or NoSQL queries, OS commands, XML parsers, SMTP headers, expression languages, and ORM queries. Injection flaws are easy to discover when examining code. Scanners and fuzzers can help attackers find injection flaws.
So they can find injection flaws with scanners without even doing anything manually. Therefore, it is easy to discover and exploit your system.
Injection can result in data loss, corruption, or disclosure to unauthorized parties, loss of accountability, or denial of access. Injection can sometimes lead to complete host takeover. The business impact depends on the needs of the application and data.
Okay, so is the application vulnerable? So an application is vulnerable to attack when, let's read each of the cases.
Asterisk user supplied data is not validated, filtered, or sanitized by the application. Asterisk dynamic queries or non-parameterized calls without context-aware escaping are used directly in the interpreter. Asterisk hostile data is used within Object Relational Mapping (ORM) search parameters to extract additional, sensitive records. Asterisk hostile data is directly used or concatenated, such that the SQL or command contains both structure and hostile data in dynamic queries, commands, or stored procedures. Some of the more common injections are SQL, NoSQL, OS command, Object Relational Mapping (ORM), LDAP, and Expression Language (L) or Object Graph Navigation Library (OGNL) injection. The concept is identical among all interpreters. Source code review is the best method of detecting if applications are vulnerable to injections, closely followed by thorough automated testing of all parameters, headers, URL, cookies, JSON, SOAP, and XML data inputs. Organizations can include static source (SAST) and dynamic application test (DAST) tools into the CI/CD pipeline to identify newly introduced injection flaws prior to production deployment.
Okay, so how can we prevent injection attacks?
Preventing injection requires keeping data separate from commands and queries.
One moment. Okay.
Asterisk the preferred option is to use a safe API, which avoids the use of the interpreter entirely or provides a parameterized interface, or migrate to use Object Relational Mapping Tools (ORMs). Note, even when parameterized, stored procedures can still introduce SQL injection if place, SQL or T-SQL concatenates queries and data, or executes hostile data with execute immediate or exec. Use positive or whitelist server-side input validation. This is not a complete defense as many applications require special characters, such as text areas or APIs for mobile applications. Asterisk for any residual dynamic queries, escape special characters using the specific escape syntax for that interpreter. Note, SQL structure such as table names, column names, and so on cannot be escaped, and thus user-supplied structure names are dangerous. This is a common issue in report writing software. Use limit and other SQL controls within queries to prevent mass disclosure of records in case of SQL injection.
Okay, there is a PDF version of top 10. Let's see if there is any additional information. Okay, introduction, release notes, application security risks, injection. Okay, I think it is same. Yeah, it is same as here. So let's continue from here. It looks better. Example attack scenarios.
Example attack scenarios. Scenario number 1, an application uses untrusted data in the construction of the following vulnerable SQL call.
Okay, at this SQL query, they are selecting everything from accounts table where customer ID equal to the parameter that is provided with get, okay, or post. And here there is no escape, there is no validation, therefore they can write anything as an ID and do whatever they want. However, if IDs are numerics, you can check that whether the provided ID is numeric or not, and if it is numeric, then there is no way to do anything harmful in this case. So never use user input like this. You have to validate or sanitize it first, or better way is writing parameterized queries. If you use parameterized query, then there is no way to do SQL injection.
Scenario number 2, similarly, an application's blind trust in frameworks may result in queries that are still vulnerable, e.g. hibernate query language HQL, query HQL query equals session, Quera from accounts.
For example, if you use SQL frameworks, then you are in danger again like this. In both cases, let's read this.
In both cases, the attacker modifies the id parameter value in their browser to send, or 1 equals 1. For example, this changes the meaning of both queries to return all the records from the accounts table. More dangerous attacks could modify or delete data, or even invoke stored procedures.
Okay, let's open an SQL injection from their external reference. Maybe there is a better example. Okay, you can read it at home. For example, here, this query executes, select everything from items table where owner has this username and item name is this text, and they can change this query to something like this, and it would return everything instead of an item name. Or here they can end the query with semicolon and write delete from items, and here end the query, that would delete everything. If you execute queries without sanitization, then you are in a big trouble. The second case is broken authentication.
Broken authentication.
So let's see the threats exploitability. And the level exploitability is 3, prevalence and detectability 2, technical is 3.
Attackers have access to hundreds of millions of valid username and password combinations for credential stuffing, default administrative account lists, automated brute force, and dictionary attack tools. Session management attacks are well understood, particularly in relation to unexpired session tokens.
Okay, so let's see the security weakness.
The prevalence of broken authentication is widespread due to the design and implementation of most identity and access controls. Session management is the bedrock of authentication and access controls, and is present in all stateful applications. Attackers can detect broken authentication using manual means and exploit them using automated tools with password lists and dictionary attacks. Attackers have to gain access to only a few accounts, or just one admin account to compromise the system. Depending on the domain of the application, this may allow money laundering, social security fraud, and identity theft, or disclose legally protected highly sensitive information.
Actually, from reading this, I have just discovered a vulnerability in one of my systems that I have developed before, and so you see it is extremely useful. I won't say what is the vulnerability I have discovered, but you have to be very careful with authentication system.
Is the application vulnerable? Confirmation of the user's identity, authentication, and session management are critical to protect against authentication-related attacks. There may be authentication weaknesses if the application permits automated attacks such as credential stuffing, where the attacker has a list of valid usernames and passwords. Permits brute force or other automated attacks. Permits default, weak, or well-known passwords, such as password1 or admin. Uses weak or ineffective credential recovery and forgot password processes, such as knowledge-based answers, which cannot be made safe. Uses plain text, encrypted, or weakly hashed passwords, CA3, 2017 sensitive data exposure. Has missing or ineffective multi-factor authentication. Exposes session IDs in the URL, e.g., URL rewriting. Does not rotate session IDs after successful login. Does not properly invalidate session IDs. User sessions or authentication tokens, particularly single sign-on SSO tokens, aren't properly invalidated during logout or a period of inactivity.
So how can we prevent broken authentication vulnerability?
Where possible, implement multi-factor authentication to prevent automated, credential stuffing, brute force, and stolen credential reuse attacks. Do not ship or deploy with any default credentials, particularly for admin users. Implement weak password checks, such as testing new or changed passwords against a list of the top 10,000 worst passwords. Align password length, complexity and rotation policies with NIST 800-63B's guidelines in Section 5.1.1 for memorized secrets or other modern, evidence-based password policies. Ensure registration, credential recovery, and API pathways are hardened against account enumeration attacks by using the same messages for all outcomes. Limit or increasingly delay failed login attempts. Log all failures and alert administrators when credential stuffing, brute force, or other attacks are detected.
Okay, this is extremely important. You have to limit the number of login tries or whatever you are using for authentication. So with this way you can prevent attackers to try every password combinations against an account, and they can't even try most commonly used password combinations as well. So limiting is extremely important, and you in some systems, some high security systems even asks bot verification when multiple login failures are detected and such. Okay.
Use a server-side, secure, built-in session manager that generates a new random session ID with high entropy after login. Session IDs should not be in the URL, be securely stored and invalidated after logout, idle, and absolute timeouts.
Okay, let's see the example attack scenarios.
Scenario number 1, credential stuffing, the use of lists of known passwords, is a common attack. If an application does not implement automated threat or credential stuffing protections, the application can be used as a password oracle to determine if the credentials are valid.
This is so easy. If you don't take any precautions for authentication trial, then they can use most commonly passwords and check them against user accounts, and probably they would have high success rate with checking hundreds of thousands of simultaneous password combinations or such if your system do not have any protection against authentication trying process.
Scenario number 2, most authentication attacks occur due to the continued use of passwords as a sole factor. Once considered best practices, password rotation and complexity requirements are viewed as encouraging users to use, and reuse, weak passwords. Organizations are recommended to stop these practices per NIST 800-63 and use multi-factor authentication.
You should not solely depend on password for authentication. Multi-factor authentication can be such as SMS verification or let's say key generators on mobile applications and such. So depending solely on password is not anymore suggested. I would say the best one is SMS verification, and mobile application based authenticators are also very strong, maybe even than SMS verification.
Scenario number 3, application session timeouts aren't set properly. A user uses a public computer to access an application. Instead of selecting log out, the user simply closes the browser tab and walks away. An attacker uses the same browser an hour later, and the user is still authenticated.
This is also true. You should not let authentication to remain after a long period of time or after user closes browser, unless the user let's say select explicitly keep me logged in feature. Okay, so this was the broken authentication. Let's continue with sensitive data exposure.
Rather than directly attacking crypto, attackers steal keys, execute man-in-the-middle attacks, or steal clear text data off the server, while in transit, or from the user's client, e.g. browser. A manual attack is generally required. Previously retrieved password databases could be brute forced by graphics processing units, GPUs. Over the last few years, this has been the most common impactful attack. The most common flaw is simply not encrypting sensitive data. When crypto is employed, weak key generation and management, and weak algorithm, protocol and cipher usage is common, particularly for weak password hashing storage techniques. For data in transit, server-side weaknesses are mainly easy to detect, but hard for data at rest. Failure frequently compromises all data that should have been protected. Typically, this information includes sensitive personal information (P) data such as health records, credentials, personal data, and credit cards, which often require protection as defined by laws or regulations such as the EU GDPR or local privacy laws.
Okay, is the application vulnerable? And let's see.
The first thing is to determine the protection needs of data in transit and at rest. For example, passwords, credit card numbers, health records, personal information and business secrets require extra protection, particularly if that data falls under privacy laws, e.g. EU's General Data Protection Regulation (GDPR), or regulations, e.g. financial data protection such as PCI Data Security Standard (PCI DSS). For all such data, is any data transmitted in clear text? This concerns protocols such as HTTP, SMTP, and FTP. External Internet traffic is especially dangerous. Verify all internal traffic, e.g. between load balancers, web servers, or back-end systems. Asterisk are any old or weak cryptographic algorithms used either by default or in older code. Asterisk are default crypto keys in use, weak crypto keys generated or reused, or is proper key management or rotation missing. Asterisk is encryption not enforced, e.g. are any user agent, browser, security directives or headers missing. Asterisk does the user agent, e.g. app, mail client, not verify if the received server certificate is valid.
Okay, so how can we prevent?
Do the following, at a minimum, and consult the references, classify data processed, stored or transmitted by an application. Identify which data is sensitive according to privacy laws, regulatory requirements, or business needs. Apply controls as per the classification. Don't store sensitive data unnecessarily. Discard it as soon as possible or use PCI DSS compliant tokenization or even truncation. Data that is not retained cannot be stolen. Make sure to encrypt all sensitive data at rest. Ensure up-to-date and strong standard algorithms, protocols, and keys are in place. Use proper key management. Encrypt all data in transit with secure protocols such as TLS with perfect forward secrecy, PFS, ciphers, cipher prioritization by the server, and secure parameters. Enforce encryption using directives like HTTP Strict Transport Security (HSTS). Disable caching for response that contain sensitive data. Store passwords using strong adaptive and salted hashing functions with a work factor, delay factor, such as Argon2, script, BCRYPT or PBKDF2. Verify independently the effectiveness of configuration and settings.
Okay, I would say that the most important thing is using HTTPS, which means using TSL when doing communication over the internet. Even if you are using SMTP or FTP, there is a secure communication. And hashing, encrypting the sensitive data. If you are using let's say secure encryption, which uses two different keys, and each side has the key, and both keys are required. End-to-end encryption, it is the best way, such as WhatsApp using. Also, when you are storing passwords in your system, user passwords, make sure that you are hashing them, but you are using salted hashes. Because if you just simply use hashes, then they can use rainbow tables to crack those password hashes. However, if you use salted hashing, then there is no way for them to crack them. And let's see some example attack scenarios.
Example attack scenarios. Scenario number 1, an application encrypts credit card numbers in a database using automatic database encryption. However, this data is automatically decrypted when retrieved, allowing a SQL injection flaw to retrieve credit card numbers in clear text.
Let's see scenario 2.
Scenario number 2, a site doesn't use or enforce TLS for all pages or supports weak encryption. An attacker monitors network traffic, e.g. at an insecure wireless network, downgrades connections from HTTPS to HTTP, intercepts requests, and steals the user's session cookie. The attacker then replays this cookie and hijacks the user's authenticated session, accessing or modifying the user's private data. Instead of the above, they could alter all transported data, e.g. the recipient of a money transfer.
Okay, so you see how much it is critical. If they can steal your cookie, then they can access your account without needing to know your password. So in the session management, there could be extra checks, such as that session will be particular to only that browser information. However, it can be also forged, or maybe for only that IP address. Then it means that you have to take extra precautions and always use a properly set up TSL. Okay.
Scenario number 3, the password database uses unsalted or simple hashes to store everyone's passwords. A file upload flaw allows an attacker to retrieve the password database. All the unsalted hashes can be exposed with a rainbow table of pre-calculated hashes. Hashes generated by simple or fast hash functions may be cracked by GPUs, even if they were salted.
Okay, so this was related to sensitive data exposure, and the next one, I will take a pause. All right, so XML External Entities, let's see.
Attackers can exploit vulnerable XML processors if they can upload XML or include hostile content in an XML document, exploiting vulnerable code, dependencies or integrations. By default, many older XML processors allow specification of an external entity, a URI that is dereferenced and evaluated during XML processing. SaaS tools can discover this issue by inspecting dependencies and configuration. DAST tools require additional manual steps to detect and exploit this issue. Manual testers need to be trained in how to test for XXE, as it not commonly tested as of 2017. These flaws can be used to extract data, execute a remote request from the server, scan internal systems, perform a denial of service attack, as well as execute other attacks. The business impact depends on the protection needs of all affected application and data.
Okay, let's see. Is the application is vulnerable?
Applications, and in particular XML-based web services or downstream integrations, might be vulnerable to attack if the application accepts XML directly or XML uploads, especially from untrusted sources, or inserts untrusted data into XML documents, which is then parsed by an XML processor. Asterisk any of the XML processors in the application or SOAP-based web services has document type definitions (DTDs) enabled. As the exact mechanism for disabling DTD processing varies by processor, it is good practice to consult a reference such as the OWASP cheat sheet XXE prevention. Asterisk if the application uses SAML for identity processing within federated security or single sign-on SSO purposes. SAML uses XML for identity assertions, and may be vulnerable. Asterisk if the application uses SOAP prior to version 1.2, it is likely susceptible to XXE attacks if XML entities are being passed to the SOAP framework. Being vulnerable to XXE attacks likely means that the application is vulnerable to denial of service attacks, including the billion laughs attack.
So what is billion laughs attack? I also heard it first time. Let's see it.
In computer security, a billion laughs attack is a type of denial of service (DOS) attack which is aimed at parsers of XML documents. 1. It is also referred to as an XML bomb or as an exponential entity expansion attack. 2.
Let's see the details.
The example attack consists of defining 10 entities, each defined as consisting of 10 of the previous entity, with the document consisting of a single instance of the largest entity, which expands to 1 billion copies of the first entity. In the most frequently cited example, the first entity is the string lol, hence the name billion laughs. At the time this vulnerability was first reported, the computer memory used by a billion instances of the string lol would likely exceed that available to the process parsing the XML. While the original form of the attack was aimed specifically at XML parsers, the term may be applicable to similar subjects as well. 1. The problem was first reported as early as 2002-3, but began to be widely addressed in 2008. 4. Defenses against this kind of attack include capping the memory allocated in an individual parser if loss of the document is acceptable, or treating entities symbolically and expanding them lazily only when, and to the extent, their content is to be used.
Okay, we get the idea. Let's continue. So how can we prevent XML attacks?
Developer training is essential to identify and mitigate XXE. Besides that, preventing XXE requires, whenever possible, use less complex data formats such as JSON, and avoiding serialization of sensitive data. Asterisk patch or upgrade all XML processors and libraries in use by the application or on the underlying operating system. Use dependency checkers. Update SOAP to SOAP 1.2 or higher. Asterisk disable XML external entity and DTD processing in all XML parsers in the application, as per the OWASP cheat sheet XXE prevention. Asterisk implement positive whitelisting, server-side input validation, filtering, or sanitization to prevent hostile data within XML documents, headers, or nodes. Asterisk verify that XML or XSL file upload functionality validates incoming XML using XSD validation or similar. Asterisk SAS tools can help detect XXE in source code, although manual code review is the best alternative in large, complex applications with many integrations. If these controls are not possible, consider using virtual patching, API security gateways, or web application firewalls (WAFs) to detect, monitor, and block XXE attacks.
So let's see an example attack scenario.
Numerous public XXE issues have been discovered, including attacking embedded devices. XXE occurs in a lot of unexpected places, including deeply nested dependencies. The easiest way is to upload a malicious XML file. If accepted, scenario number 1, the attacker attempts to extract data from the server.
So how does the attacker do that? There is entity XXA system file etc password. Okay, so with this way they may try to extract data from servers. Therefore, you have to check and sanitize what can be done. So whitelist using is the best approach.
Scenario number 2, an attacker probes the server's private network by changing the above entity line to.
So they can try to probe a private network using 192.168 is used for local networks, local area network, and here they are trying to probe the private network. And the scenario 3.
Scenario number 3, an attacker attempts a denial of service attack by including a potentially endless file.
Okay, so let's continue. Number 5, broken access control.
Exploitation of access control is a core skill of attackers. SAST and DAST tools can detect the absence of access control but cannot verify if it is functional when it is present. Access control is detectable using manual means, or possibly through automation for the absence of access controls in certain frameworks.
So, security weakness of access control.
Access control weaknesses are common due to the lack of automated detection and lack of effective functional testing by application developers. Access control detection is not typically amenable to automated static or dynamic testing. Manual testing is the best way to detect missing or ineffective access control, including HTTP method, get versus put, etc., controller, direct object references, etc. The technical impact is attackers acting as users or administrators, or users using privileged functions, or creating, accessing, updating or deleting every record. The business impact depends on the protection needs of the application and data.
Okay, so how can we detect if the application is vulnerable or not?
Is the application vulnerable? Access control enforces policy such that users cannot act outside of their intended permissions. Failures typically lead to unauthorized information disclosure, modification or destruction of all data, or performing a business function outside of the limits of the user. Common access control vulnerabilities include bypassing access control checks by modifying the URL, internal application state, or the HTML page, or simply using a custom API attack tool. Asterisk allowing the primary key to be changed to another's user's record, permitting viewing or editing someone else's account. Asterisk elevation of privilege. Acting as a user without being logged in, or acting as an admin when logged in as a user. Asterisk metadata manipulation, such as replaying or tampering with a JSON Web Token (JWT) access control token or a cookie or hidden field manipulated to elevate privileges, or abusing JWT invalidation. Asterisk CORS misconfiguration allows unauthorized API access. Asterisk force browsing to authenticated pages as an unauthenticated user or to privileged pages as a standard user. Accessing API with missing access controls for post, put and delete.
Okay, so how can we prevent broken access control?
Access control is only effective if enforced in trusted server-side code or serverless API, where the attacker cannot modify the access control check or metadata. With the exception of public resources, deny by default. Asterisk implement access control mechanisms once and reuse them throughout the application, including minimizing CORS usage. Asterisk model access controls should enforce record ownership, rather than accepting that the user can create, read, update, or delete any record. Asterisk unique application business limit requirements should be enforced by domain models. Asterisk disable web server directory listing and ensure file metadata e.g. .git and backup files are not present within web routes. Asterisk log access control failures, alert admins when appropriate e.g. repeated failures. Asterisk rate limit API and controller access to minimize the harm from automated attack tooling. Asterisk JWT tokens should be invalidated on the server after logout. Developers and QA staff should include functional access control unit and integration tests. Example attack scenarios. Scenario number 1, the application uses unverified data in a SQL call that is accessing account information.
Okay, let's try to understand it. So it requests get parameter account, results parameter execute query. Okay, let's continue.
An attacker simply modifies the ACCT parameter in the browser to send whatever account number they want. If not properly verified, the attacker can access any user's account.
Okay, so this is about trusting the user input, and even if that input is hidden. This was a case in my first developed web application. I have trusted post data of the user because it is hidden, as you know, and it is posted with hidden web forms. However, it was one of the most easy way to modify data in an unwanted way. Therefore, after that, I have learned that never trust any user sent data. Always verify it, always validate it, always sanitize it. Okay. So in this case, it is about trusting the user input data.
Scenario number 2, an attacker simply force browses to target URLs. Admin rights are required for access to the admin page.
Also, never think as that your hidden pages or APIs, web services cannot be found. They can be found, they can be leaked somehow. Therefore, make sure that even those hidden pages, even if those pages or services or APIs are hidden, you are using the standard authorization and authentication. Okay.
If an unauthenticated user can access either page, it's a flaw. If a non-admin can access the admin page, this is a flaw.
Okay, so okay, let's continue. Security misconfiguration. So
Attackers will often attempt to exploit unpatched flaws or access default accounts, unused pages, unprotected files and directories, etc. to gain unauthorized access or knowledge of the system.
so security weakness.
Security misconfiguration can happen at any level of an application stack, including the network services, platform, web server, application server, database, frameworks, custom code, and pre-installed virtual machines, containers, or storage. Automated scanners are useful for detecting misconfigurations, use of default accounts or configurations, unnecessary services, legacy options, etc. Such flaws frequently give attackers unauthorized access to some system data or functionality. Occasionally, such flaws result in a complete system compromise. The business impact depends on the protection needs of the application and data.
So is the application vulnerable?
Is the application vulnerable? The application might be vulnerable if the application is missing appropriate security hardening across any part of the application stack, or improperly configured permissions on cloud services. Unnecessary features are enabled or installed, e.g. unnecessary ports, services, pages, accounts, or privileges. Default accounts and their passwords still enabled and unchanged. Error handling reveals stack traces or other overly informative error messages to users. For upgraded systems, latest security features are disabled or not configured securely. The security settings in the application servers, application frameworks e.g. struts, Spring, ASP.NET, libraries, databases, etc. not set to secure values. The server does not send security headers or directives or they are not set to secure values. Asterisk the software is out of date or vulnerable. CA9, 2017 using components with known vulnerabilities. Without a concerted, repeatable application security configuration process, systems are at a higher risk.
So how to prevent security misconfiguration?
How to prevent secure installation processes should be implemented, including, asterisk a repeatable hardening process that makes it fast and easy to deploy another environment that is properly locked down. Development, QA, and production environments should all be configured identically, with different credentials used in each environment. This process should be automated to minimize the effort required to set up a new secure environment. Asterisk a minimal platform without any unnecessary features, components, documentation, and samples. Remove or do not install unused features and frameworks. Asterisk a task to review and update the configurations appropriate to all security notes, updates and patches as part of the patch management process. CA9, 2017 using components with known vulnerabilities. In particular, review cloud storage permissions, e.g. S3 bucket permissions. Asterisk a segmented application architecture that provides effective, secure separation between components or tenants, with segmentation, containerization, or cloud security groups ACLs. Asterisk sending security directives to clients, e.g. security headers. Asterisk an automated process to verify the effectiveness of the configurations and settings in all environments.
Okay, let's see the example attack scenarios. The scenario 1.
Scenario number 1, the application server comes with sample applications that are not removed from the production server. These sample applications have known security flaws attackers use to compromise the server. If one of these applications is the admin console, and default accounts weren't changed, the attacker logs in with default passwords and takes over.
Okay, scenario 2.
Scenario number 2, directory listing is not disabled on the server. An attacker discovers they can simply list directories. The attacker finds and downloads the compiled Java classes, which they decompile and reverse engineer to view the code. The attacker then finds a serious access control flaw in the application.
This is really important. You should never allow directory listing unless it is explicitly necessary. This is really important.
Scenario number 3, the application server's configuration allows detailed error messages, e.g. stack traces, to be returned to users. This potentially exposes sensitive information or underlying flaws such as component versions that are known to be vulnerable. Scenario number 4, a cloud service provider has default sharing permissions open to the internet by other CSP users. This allows sensitive data stored within cloud storage to be accessed.
Okay, scenario number 3 is another thing that I have encountered. Sometimes even in government websites, I see that they are displaying the full error, either in PHP or either in ASP.NET, and it is extremely wrong. Okay, so you should handle the unhandled exception message and do not show clients, browsers the full exception stack. For example, output ASP.NET. I am sure that you have even encountered them such as this. For example, an example message shown here. Even on government websites or even on corporate websites, sometimes I see they don't hide the full exception message. So this can lead data exposure, like said here, and it can cause security vulnerabilities. Okay, let's continue. And this is another very important one.
Cross-site scripting XSS.
And this is also a very common one.
Automated tools can detect and exploit all three forms of XSS, and there are freely available exploitation frameworks. XSS is the second most prevalent issue in the OWASP top 10, and is found in around 2/3 of all applications. Automated tools can find some XSS problems automatically, particularly in mature technologies such as PHP, J2EE, JSP, and ASP.NET. The impact of XSS is moderate for reflected and DOM XSS, and severe for stored XSS, with remote code execution on the victim's browser, such as stealing credentials, sessions, or delivering malware to the victim.
Okay, so
Is the application vulnerable? There are three forms of XSS, usually targeting users' browsers. Reflected XSS, the application or API includes unvalidated and unescaped user input as part of HTML output. A successful attack can allow the attacker to execute arbitrary HTML and JavaScript in the victim's browser. Typically, the user will need to interact with some malicious link that points to an attacker-controlled page, such as malicious watering hole websites, advertisements, or similar. Stored XSS, the application or API stores unsanitized user input that is viewed at a later time by another user or an administrator. Stored XSS is often considered a high or critical risk. DOM XSS, JavaScript frameworks, single-page applications, and APIs that dynamically include attacker-controllable data to a page are vulnerable to DOM XSS. Ideally, the application would not send attacker-controllable data to unsafe JavaScript APIs. Typical XSS attacks include session stealing, account takeover, MFA bypass, DOM node replacement or defacement, such as Trojan login panels, attacks against the user's browser such as malicious software downloads, key logging, and other client-side attacks.
So you see they are extremely serious and common and easy to achieve if the user input is not sanitized. Okay.
How to prevent? Preventing XSS requires separation of untrusted data from active browser content. This can be achieved by using frameworks that automatically escape XSS by design, such as the latest Ruby on Rails, React.js. Learn the limitations of each framework's XSS protection and appropriately handle the use cases which are not covered. Escaping untrusted HTTP request data based on the context in the HTML output body, attribute, JavaScript, CSS, or URL will resolve reflected and stored XSS vulnerabilities. The OWASP cheat sheet XSS Prevention has details on the required data escaping techniques. Applying context-sensitive encoding when modifying the browser document on the client side acts against DOM XSS. When this cannot be avoided, similar context-sensitive escaping techniques can be applied to browser APIs as described in the OWASP cheat sheet. DOM-based XSS Prevention. Enabling a Content Security Policy (CSP) as a defense in-depth mitigating control against XSS. It is effective if no other vulnerabilities exist that would allow placing malicious code via local file includes e.g. path traversal overwrites or vulnerable libraries from permitted content delivery networks.
Okay, so I will show you how to escape properly in ASP.NET. You can escape in ASP.NET with something like this. Let me show you. Okay. I think it was done with semicolon, something like this. You can use HTTP to the HTML encode, but I think here, you see, if you write your code like this in ASP.NET, it automatically encodes your input, therefore it is getting escaped. I think there's an article related to it here. Here, new syntax for HTML encoding output. If you write your output within like this in ASP.NET, then it will be encoded and it will prevent XSS attacks.
Today's post covers a small, but very useful, new syntax feature being introduced with ASP.NET 4, which is the ability to automatically HTML encode output within code nuggets. This helps protect your applications and sites against cross-site script injection (XSS) and HTML injection attacks, and enables you to do so using a nice, concise syntax.
And instead of writing like this with a equal sign, you write like this, and it's automatically encodes your input. You see here instead of this one. Okay, and it may change according to other programming languages, of course. So they have some cross-site script preventing cheat sheet. You see it is under OWASP cheat sheet series. You can read this as well. It looks like pretty detailed. And there is another article, DOM-based XSS prevention sheets. And there are other cheat sheets such as file upload, error handling, .NET security, for example. Let's read. This page intends to provide quick, basic .NET security tips for developers, updating framework, security announcements, data access, use parameterized SQL. This is really important. When you do a query against the database, you should use parameterized query like this. It uses SQL command instead of directly executing the command itself. And you can also use entity framework to prevent SQL injection. I am showing how to use entity framework on our object-oriented programming language course. And you can also use encryption, but it says never ever write your own encryption. Use Windows Data Protection API, lockdown configuration file, and use HTTPS, require SSL, implement custom errors, make sure tracing turn it off, HTML validation and encoding, forms authentication, MVC guidelines, injection, and other things. They also show examples. Validate anti-forgery token, auto validate anti-forgery token. Okay. Cross scripting, components with non-variables, insufficient logging and monitoring, and log all errors in the application. Application use exception handler. I also have something like this in my websites that I develop. There are also other ones such as PHP configuration, REST security, SQL injection prevention, TLS cipher string, and actually you should have idea in all of these cheat sheets if you are developing application based on them. For example, deserialization. I also use serialization and deserialization in my C# applications. Okay, and let's continue to example attack scenarios. So scenario 1.
Scenario number 1, the application uses untrusted data in the construction of the following HTML snippet without validation or escaping.
Okay, so there is input name, credit card type, text value, request parameter CC. The attacker modifies the CC parameter in the browser to get attacker.com CGI bin cookie CGI foo document cookie script. Let's read it.
This attack causes the victim's session ID to be sent to the attacker's website, allowing the attacker to hijack the user's current session. Note, attackers can use XSS to defeat any automated cross-site request forgery (CSRF) defense the application might employ.
Okay, and that was a good example. Let's do insecure deserialization. Okay, I will take a pause. Okay, let's continue with insecure deserialization.
Exploitation of deserialization is somewhat difficult, as off-the-shelf exploits rarely work without changes or tweaks to the underlying exploit code.
So you see, its exploitability is only 1.
This issue is included in the top 10 based on an industry survey and not on quantifiable data. Some tools can discover deserialization flaws, but human assistance is frequently needed to validate the problem. It is expected that prevalence data for deserialization flaws will increase as tooling is developed to help identify and address it. The impact of deserialization flaws cannot be overstated. These flaws can lead to remote code execution attacks, one of the most serious attacks possible. The business impact depends on the protection needs of the application and data. Is the application vulnerable? Applications and APIs will be vulnerable if they deserialize hostile or tampered objects supplied by an attacker. This can result in two primary types of attacks: object and data structure related attacks, where the attacker modifies application logic or achieves arbitrary remote code execution if there are classes available to the application that can change behavior during or after deserialization. Typical data tampering attacks such as access control related attacks, where existing data structures are used but the content is changed. Serialization may be used in applications for remote and inter-process communication (RPC, IPC), wire protocols, web services, message brokers, caching, persistence databases, cache servers, file systems HTTP cookies, HTML form parameters, API authentication tokens. How to prevent. The only safe architectural pattern is not to accept serialized objects from untrusted sources or to use serialization mediums that only permit primitive data types. If that is not possible, consider one of more of the following: implementing integrity checks such as digital signatures on any serialized objects to prevent hostile object creation or data tampering. Enforcing strict type constraints during deserialization before object creation, as the code typically expects a definable set of classes. Bypasses to this technique have been demonstrated, so reliance solely on this is not advisable. Isolating and running code that deserializes in low privilege environments when possible. Log deserialization exceptions and failures, such as where the incoming type is not the expected type, or the deserialization throws exceptions. Restricting or monitoring incoming and outgoing network connectivity from containers or servers that deserialize. Monitoring deserialization, alerting if a user deserializes constantly.
Okay, example attack scenarios. Let's see them.
Scenario number 1, a React application calls a set of Spring Boot microservices. Being functional programmers, they tried to ensure that their code is immutable. The solution they came up with is serializing user state and passing it back and forth with each request. An attacker notices the R00 Java object signature, and uses the Java serial killer tool to gain remote code execution on the application server.
And the scenario 2.
Scenario number 2, a PHP forum uses PHP object serialization to save a super cookie containing the user's user ID, role, password hash, and other state.
Such as this one. So I think we can say which can be the user ID. Any of them.
An attacker changes the serialized object to give themselves admin privileges.
So if the server is accepting this serialization without any check and control, then you can just modify the values and send to the server and gain access. Okay, this is a very simple mistake, but if it happens, then they can get admin privileges and other things. Okay, number 9, using components with known vulnerabilities.
While it is easy to find already written exploits for many known vulnerabilities, other vulnerabilities require concentrated effort to develop a custom exploit. Prevalence of this issue is very widespread. Component-heavy development patterns can lead to development teams not even understanding which components they use in their application or API, much less keeping them up to date. Some scanners such as Retire.js help in detection, but determining exploitability requires additional effort. While some known vulnerabilities lead to only minor impacts, some of the largest breaches to date have relied on exploiting known vulnerabilities in components. Depending on the assets you are protecting, perhaps this risk should be at the top of the list.
I have seen many times that there were vulnerable block plugins, such as one of the most famous. Okay, WordPress. There were many vulnerable WordPress plugins. Okay, let's find an article. Okay, this is the recent one.
Hackers are reportedly exploiting vulnerabilities in over 10 WordPress plugins in order to backdoor sites with Rouge admin accounts. This is an escalation of an attack that was reported on back in July, in which attackers were hijacking sites to serve ads, scams, and malicious app downloads. Now, the same hacker group is taking complete control of vulnerable sites using similar tactics. ZDNet reports as of August 20 the hacker group modified the malicious code planted on hacked sites. The malicious code was modified to detect when the site owner logged into their own site. Upon logging in, the code used the owner's admin privileges to create a new admin account named WP Services, which is linked to the email address wpservices@yandex.com.
So you see, if the plugin you are using is vulnerable and you don't update it and you don't fix the error, the hackers can easily make automatic scans for known vulnerability having website, blogs, platforms, services, anything, and automatically detect and hack your system and exploit it to their benefit. Okay, so this is the real issue in ready components using systems. Okay, let's read it.
Is the application vulnerable? You are likely vulnerable, if you do not know the versions of all components you use, both client-side and server-side. This includes components you directly use as well as nested dependencies. Asterisk if software is vulnerable, unsupported, or out of date. This includes the OS, Web Application Server, Database Management System (DBMS), applications, APIs and all components, runtime environments, and libraries. Asterisk if you do not scan for vulnerabilities regularly and subscribe to security bulletins related to the components you use. Asterisk if you do not fix or upgrade the underlying platform, frameworks, and dependencies in a risk-based, timely fashion. This commonly happens in environments when patching is a monthly or quarterly task under change control, which leaves organizations open to many days or months of unnecessary exposure to fixed vulnerabilities. Asterisk if software developers do not test the compatibility of updated, upgraded, or patched libraries. Asterisk if you do not secure the component's configurations. CA6, 2017 Security Misconfiguration.
Okay. And how to prevent such vulnerability?
There should be a patch management process in place to remove unused dependencies, unnecessary features, components, files, and documentation. Continuously inventory the versions of both client-side and server-side components, e.g. frameworks, libraries, and their dependencies using tools like versions, dependency check, retire, JS, etc. Continuously monitor sources like CVE and NVD for vulnerabilities in the components. Use software composition analysis tools to automate the process. Subscribe to email alerts for security vulnerabilities related to components you use. Only obtain components from official sources over secure links. Prefer signed packages to reduce the chance of including a modified, malicious component. Monitor for libraries and components that are unmaintained or do not create security patches for older versions. If patching is not possible, consider deploying a virtual patch to monitor, detect, or protect against the discovered issue. Every organization must ensure that there is an ongoing plan for monitoring, triaging, and applying updates or configuration changes for the lifetime of the application or portfolio. Example attack scenarios. Scenario number 1, components typically run with the same privileges as the application itself, so flaws in any component can result in serious impact. Such flaws can be accidental, e.g. coding error, or intentional, e.g. backdoor in component. Some example exploitable component vulnerabilities discovered are CVE 20175638, a struts2 remote code execution vulnerability that enables execution of arbitrary code on the server, has been blamed for significant breaches. While Internet of Things (IoT) are frequently difficult or impossible to patch, the importance of patching them can be great, e.g. biomedical devices. There are automated tools to help attackers find unpatched or misconfigured systems. For example, the Shodan IoT search engine can help you find devices that still suffer from Heartbleed vulnerability that was patched in April 2014.
Okay, and the last part of the top 10 list.
Insufficient logging and monitoring. Exploitation of insufficient logging and monitoring is the bedrock of nearly every major incident. Attackers rely on the lack of monitoring and timely response to achieve their goals without being detected. This issue is included in the top 10 based on an industry survey. One strategy for determining if you have sufficient monitoring is to examine the logs following penetration testing. The tester's actions should be recorded sufficiently to understand what damages they may have inflicted. Most successful attacks start with vulnerability probing. Allowing such probes to continue can raise the likelihood of successful exploit to nearly 100%. In 2016, identifying a breach took an average of 191 days, plenty of time for damage to be inflicted.
So not only discovering the vulnerability, but also the time left for exploiters, for hacker to exploit your system matters. So if you have necessary tools, one moment. Okay. All right. So is the application vulnerable?
Insufficient logging, detection, monitoring and active response occurs anytime, auditable events, such as logins, failed logins, and high-value transactions are not logged. Warnings and errors generate no, inadequate, or unclear log messages. Logs of applications and APIs are not monitored for suspicious activity. Logs are only stored locally. Appropriate alerting thresholds and response escalation processes are not in place or effective. Penetration testing and scans by DAST tools such as OWASP ZAP do not trigger alerts. The application is unable to detect, escalate, or alert for active attacks in real time or near real time. You are vulnerable to information leakage if you make logging and alerting events visible to a user or an attacker. CA3, 2017 Sensitive Data Exposure.
Okay, there are vulnerability scanning tools. Let's see if not any of them are free. Yes, there are some free ones. There's open source ones, open source. So let's see them. Free, simple, distributed, intelligent, powerful, friendly. And how does it work? It scans the website, I guess. License program. There are also some open source ones. Grabber. Okay, let's see. Okay, so it scans cross-site scripting, SQL injection, file inclusion, backup files check, simple Ajax check, and such. And Grendel scan, which looks pretty outdated right now. Let's see this one. There is license. Okay, so you can use some ready tools to scan vulnerabilities in your system. You see there are so many ones, and I don't know which one of them are best. Some of them are open source, free. For example, there is this one. And Python powered open source. There's a blog of it. Let's look. Documentation. And such. Okay, so you get the idea. And how to prevent.
How to prevent as per the risk of the data stored or processed by the application, ensure all login, access control failures, and server-side input validation failures can be logged with sufficient user context to identify suspicious or malicious accounts, and held for sufficient time to allow delayed forensic analysis. Ensure that logs are generated in a format that can be easily consumed by a centralized log management solutions. Ensure high-value transactions have an audit trail with integrity controls to prevent tampering or deletion, such as append-only database tables or similar. Establish effective monitoring and alerting such that suspicious activities are detected and responded to in a timely fashion. Establish or adopt an incident response and recovery plan, such as NIST 800-61 Rev 2 or later. There are commercial and open source application protection frameworks such as OWASP App Sensor, Old Wiki, web application firewalls such as Mod Security with the OWASP Mod Security Core rule set, and log correlation software with custom dashboards and alerting.
Okay, let's see some example attack scenarios.
Scenario number 1, an open-source project forum software run by a small team was hacked using a flaw in its software. The attackers managed to wipe out the internal source code repository containing the next version, and all of the forum contents. Although source could be recovered, the lack of monitoring, logging or alerting led to a far worse breach. The forum software project is no longer active as a result of this issue. Scenario number 2, an attacker uses scans for users using a common password. They can take over all accounts using this password. For all other users, this scan leaves only one false login behind. After some days, this may be repeated with a different password. Scenario number 3, a major US retailer reportedly had an internal malware analysis sandbox analyzing attachments. The sandbox software had detected potentially unwanted software, but no one responded to this detection. The sandbox had been producing warnings for some time before the breach was detected due to fraudulent card transactions by an external bank.
Okay, so we have seen the top 10 application security risks. Of course, there could be more security risks as well. And now we will see injection attacks. I think which one is the most dangerous one. Okay, so let's start.
Injection attacks refer to a broad class of attack vectors. In an injection attack, an attacker supplies untrusted input to a program. This input gets processed by an interpreter as part of a command or query. In turn, this alters the execution of that program. Injections are amongst the oldest and most dangerous attacks aimed at web applications. They can lead to data theft, data loss, loss of data integrity, denial of service, as well as full system compromise. The primary reason for injection vulnerabilities is usually insufficient user input validation. This attack type is considered a major problem in web security. It is listed as the number 1 web application security risk in the OWASP Top 10, and for a good reason. Injection attacks, particularly SQL injections, SQL attacks, and cross-site scripting (XSS), are not only very dangerous but also widespread, especially in legacy applications. What makes injection vulnerabilities particularly scary is that the attack surface is enormous, especially for XSS and SQL injection vulnerabilities. Furthermore, injection attacks are a very well understood vulnerability class. This means that there are many freely available and reliable tools that allow even inexperienced attackers to abuse these vulnerabilities automatically.
So injection attacks are number 1 and cross-site scripting attacks are number 2. Vulnerabilities and dangers for web applications. So let's see the types of attacks.
Types of injection attacks: SQL injection (SQLI) and cross-site scripting (XSS) are the most common injection attacks, but they are not the only ones. The following is a list of common injection attack types.
Okay, let's start with code injection.
Code injection or remote code execution (RCE) enables the attacker to execute malicious code as a result of an injection attack. Code injection attacks are different than command injection attacks. Attacker capabilities depend on the limits of the server-side interpreter, for example, PHP, Python, and more. In some cases, an attacker may be able to escalate from code injection to command injection. Typically, code injection occurs when an application evaluates code without validating it first. The following is a source code of an example PHP application with a code injection bug.
So you see, the PHP gets the code with get method and then evaluate it without validating it. You see, it just runs it.
Based on the above example, an attacker could use the following construct to execute arbitrary PHP code. As a result, the PHP info page would be displayed.
Okay, and then
OS command execution. An attacker may be able to escalate a code injection vulnerability even further by executing arbitrary operating system commands on the server. Based on the example above, the attacker can execute the whomi shell command using the system function in PHP.
Like this.
Once an attacker is able to execute OS commands, they could attempt to use a web shell or install other malware. From there, an attacker may even attempt to compromise other internal systems. Finding and preventing code injection vulnerabilities. Fortunately, it's easy to test if your website or web.
Okay, there is some advertisement here.
If you find code injection vulnerabilities, the most effective method to eliminate them is to avoid code evaluation at all costs unless absolutely and explicitly necessary, i.e., you cannot achieve the same result without code evaluation. Generally, evaluating code that contains user input is a dangerous way and you almost always get in trouble. There is even a common mantra for the PHP eval function: eval is evil. If code evaluation is necessary, you must use strong user input validation. It requires as many restrictions for untrusted data as possible. Remember that attackers may use many methods to go around input validation conditions.
I would say that never execute code taken from users. It's also said here, find another solution, find another way, or whitelist the code.
Note, some sources use the term code injection to refer to all types of attacks that inject any kind of code into the web application. According to those sources, there are many types of code injection attacks including Sql Injection attacks, cross-site scripting Xss attacks also called HTML script injection or JavaScript injection, and even command injection attacks also called shell injection. Acunetics, like OWASP, uses the term code injection to refer only to remote code execution, also called dynamic evaluation.
Okay, let's continue.
What are Crlf injection attacks? A Crlf injection attack is one of several types of injection attacks. It can be used to escalate to more malicious attacks such as cross-site scripting XSS, page injection, web cache poisoning, cache-based defacement, and more. A Crlf injection vulnerability exists if an attacker can inject the Crlf characters into a web application, for example using a user input form or an HTTP request. The Crlf abbreviation refers to carriage return and line feed. CR and LF are special characters ASCII 13 and 10 respectively, also referred to as RN, that are used to signify the end of line EOL. The Crlf sequence is used in operating systems including Windows but not Linux, Unix, and Internet protocols including HTTP. There are two most common uses of Crlf injection attacks: log poisoning and HTTP response splitting. In the first case, the attacker falsifies log file entries by inserting an end of a line and an extra line. This can be used to hide other attacks or to confuse system administrators. In the second case, Crlf injection is used to add HTTP headers to the HTTP response and, for example, perform an XSS attack that leads to information disclosure. A similar technique, called email header injection, may be used to add SMTP headers to emails.
Okay, so there is also email injection attacks. And is it? Yeah, it's here.
What is HTTP response splitting? The HTTP protocol uses the Crlf character sequence to signify where one header ends and another begins. It also uses it to signify where headers end and the website content begins. If the attacker inserts a single Crlf, they can add a new header. If it is, for example, a location header, the attacker can redirect the user to a different website. Criminals may use this technique for phishing or defacing. This technique is often called HTTP header injection. If the attacker inserts a double CRLF, they can prematurely terminate HTTP headers and inject content before the actual website content. The injected content can contain JavaScript code. It can also be formulated so that the actual website content coming from the web server is ignored by the web browser. This is how HTTP response splitting is used in combination with cross-site scripting XSS. The following simplified example uses CRLF to add a fake HTTP response header, content length 0. This causes the web browser to treat this as a terminated response and begin parsing a new response. Add a fake HTTP response, HTTP 1.1200 OK. This begins the new response. Add another fake HTTP response header, content type, text, HTML. This is needed for the web browser to properly parse the content. Add yet another fake HTTP response header, content length 25. This causes the web browser to only parse the next 25 bytes. Add page content with an XSS, less than script greater than alert 1, less than, script greater than. This content has exactly 25 bytes. Because of the content length header, the web browser ignores the original content that comes from the web server. Variations of this attack can be used to poison proxy or web caches in order to get the cache to serve the attacker's content to other users. Finding and mitigating CRLF injections. The impact of CRLF injections may seem to be limited. CRLF injections are not even mentioned in the OWASP Top 10 2017 Web Application Security List. However, attackers can effectively use CRLF injections to escalate to much more serious attacks that exploit other web application vulnerabilities. Therefore, you should treat CRLF injection vulnerabilities seriously. Fortunately, it's easy to test if your website or web application is vulnerable to CRLF.
Okay, so let's continue.
CRLF injection vulnerabilities are usually mitigated by web frameworks automatically. Even if the vulnerability is not mitigated, it is very simple to fix. Option 1, rework your code so that content supplied by the user is never used directly in the HTTP stream. Option 2, strip any newline characters before passing content into the HTTP header. Option 3, encode the data that you pass into HTTP headers. This will effectively scramble the CR and LF codes if the attacker attempts to inject them. How to prevent CRLF injections.
Dur kızım.
CRLF injection vulnerabilities are usually mitigated by web frameworks automatically. Even if the vulnerability is not mitigated, it is very simple to fix.
Okay, step 1, don't trust user input. This is our golden rule. Never ever trust user input.
Rework your code so that content supplied by the user is never used directly in the HTTP stream.
Step 2, strip new lines. Strip any new line characters before passing content into the HTTP header. Step 3, encode data. Encode the data that you pass into HTTP headers. This will effectively scramble the CR and LF codes if the attacker attempts to inject them. And okay, so these are the solutions. And cross-site scripting, I will take a pause here. Alright, so cross-site scripting, we have already seen that. However, let's repeat, no harm.
Cross-site scripting XSS. Cross-site scripting XSS is a client-side code injection attack. The attacker aims to execute malicious scripts in a web browser of the victim by including malicious code in a legitimate web page or web application. The actual attack occurs when the victim visits the web page or web application that executes the malicious code. The web page or web application becomes a vehicle to deliver the malicious script to the user's browser. Vulnerable vehicles that are commonly used for cross-site scripting attacks are forums, message boards, and web pages that allow comments. A web page or web application is vulnerable to XSS if it uses unsanitized user input in the output that it generates. This user input must then be parsed by the victim's browser. XSS attacks are possible in VB-Script, ActiveX, Flash, and even CSS. However, they are most common in JavaScript, primarily because JavaScript is fundamental to most browsing experiences. Isn't cross-site scripting the user's problem? If an attacker can abuse an XSS vulnerability on a web page to execute arbitrary JavaScript in a user's browser, the security of that vulnerable website or vulnerable web application and its users has been compromised. XSS is not the user's problem like any other security vulnerability. If it is affecting your users, it affects you. Cross-site scripting may also be used to deface a website instead of targeting the user. The attacker can use injected scripts to change the content of the website or even redirect the browser to another web page, for example, one that contains malicious code. What can the attacker do with JavaScript? XSS vulnerabilities are perceived as less dangerous than, for example, SQL injection vulnerabilities. Consequences of the ability to execute JavaScript on a web page may not seem dire at first. Most web browsers run JavaScript in a very tightly controlled environment. JavaScript has limited access to the user's operating system and the user's files. However, JavaScript can still be dangerous if misused as part of malicious content. Malicious JavaScript has access to all the objects that the rest of the web page has access to. This includes access to the user's cookies. Cookies are often used to store session tokens. If an attacker can obtain a user's session cookie, they can impersonate that user, perform actions on behalf of the user, and gain access to the user's sensitive data. JavaScript can read the browser DOM and make arbitrary modifications to it. Luckily, this is only possible within the page where JavaScript is running. JavaScript can use the XML HTTP request object to send HTTP requests with arbitrary content to arbitrary destinations. JavaScript in modern browsers can use HTML5 APIs. For example, it can gain access to the user's geolocation, webcam, microphone, and even specific files from the user's file system. Most of these APIs require user opt-in, but the attacker can use social engineering to go around that limitation.
They can even do Bitcoin mining on your browser, or they can use your browser as a part of a zombie network to do DDoS attacks and such. So you see, it is not that it is also dangerous, maybe not as much as SQL injection, but still it can do a lot of harm to the user.
The above, in combination with social engineering, allow criminals to pull off advanced attacks including cookie theft, planting Trojans, keylogging,
Okay, sorry about the interruption. Okay.
The above, in combination with social engineering, allow criminals to pull off advanced attacks including cookie theft, planting Trojans, keylogging, phishing, and identity theft. XSS vulnerabilities provide the perfect ground to escalate attacks to more serious ones. Cross-site scripting can also be used in conjunction with other types of attacks, for example, cross-site request forgery (CSRF). There are several types of cross-site scripting attacks: stored, persistent XSS, reflected, non-persistent XSS, and DOM-based XSS. You can read more about them in an article titled Types of XSS.
Yeah, let's check it out too. And let's see. Okay, there is stored XSS, reflected. Okay, let's read them.
Stored XSS, persistent XSS. The most damaging type of XSS is stored XSS, persistent XSS. An attacker uses stored XSS to inject malicious content, referred to as the payload, most often JavaScript code, into the target application. If there is no input validation, this malicious code is permanently stored, persisted, by the target application, for example within a database. For example, an attacker may enter a malicious script into a user input field such as a blog comment field or in a forum post. When a victim opens the affected web page in a browser, the XSS attack payload is served to the victim's browser as part of the HTML code, just like a legitimate comment would. This means that victims will end up executing the malicious script once the page is viewed in their browser. Reflected XSS, non-persistent XSS. The second and the most common type of XSS is reflected XSS, non-persistent XSS. In this case, the attacker's payload has to be a part of the request that is sent to the web server. It is then reflected back in such a way that the HTTP response includes the payload from the HTTP request. Attackers use malicious links, phishing emails, and other social engineering techniques to lure the victim into making a request to the server. The reflected XSS payload is then executed in the user's browser. Reflected XSS is not a persistent attack, so the attacker needs to deliver the payload to each victim. These attacks are often made using social networks. DOM-based XSS. DOM-based XSS is an advanced XSS attack. It is possible if the web application's client-side scripts write data provided by the user to the document object model (DOM). The data is subsequently read from the DOM by the web application and outputted to the browser. If the data is incorrectly handled, an attacker can inject a payload, which will be stored as part of the DOM and executed when the data is read back from the DOM. A DOM-based XSS attack is often a client-side attack and the malicious payload is never sent to the server. This makes it even more difficult to detect for web application firewalls (WAFs) and security engineers who analyze server logs because they will never even see the attack. DOM objects that are most often manipulated include the URL, document URL, the anchor part of the URL, location, hash, and the referrer, document, referrer.
Okay, and there was something else. Cross-site forgery. Is it here? No, let's look at this one as well.
Csrf attacks, anatomy, prevention, and Csrf tokens. Cross-site request forgery, also known as CSRF, Csrf, or XSRF, is an attack whereby an attacker tricks a victim into performing actions on their behalf. The impact of the attack depends on the level of permissions that the victim has. Such attacks take advantage of the fact that a website completely trusts a user once it can confirm that the user is indeed who they say they are. Cross-site request forgery is considered a sleeping giant in the world of web application security. It is often not taken as seriously as it should, even though it can prove to be a stealthy and powerful attack if executed properly. It is also a common attack, which is why it has secured a spot on the OWASP top 10 list several times in a row. However, an exploited cross-site scripting vulnerability (XSS) is more of a risk than any CSRF vulnerability because CSRF attacks have a major limitation. CSRF only allows for state changes to occur and therefore the attacker cannot receive the contents of the HTTP response. How are CSRF attacks executed? There are two main parts to executing a cross-site request forgery attack. The first one is tricking the victim into clicking a link or loading a page. This is normally done through social engineering and malicious links. The second part is sending a crafted, legitimate-looking request from the victim's browser to the website. The request is sent with values chosen by the attacker, including any cookies that the victim has associated with that website. This way, the website knows that this victim can perform certain actions on the website. Any request sent with these HTTP credentials or cookies will be considered legitimate, even though the victim would be sending the request on the attacker's command. When a request is made to a website, the victim's browser checks if it has any cookies that are associated with the origin of that website and that need to be sent with the HTTP request. If so, these cookies are included in all requests sent to this website. The cookie value typically contains authentication data, and such cookies represent the user's session. This is done to provide the user with a seamless experience, so they are not required to authenticate again for every page that they visit. If the website approves of the session cookie and considers the user session still valid, an attacker may use Csrf to send requests as if the victim was sending them. The website is unable to distinguish between requests being sent by the attacker and those sent by the victim, since requests are always being sent from the victim's browser with their own cookie. A Csrf attack simply takes advantage of the fact that the browser sends the cookie to the website automatically with each request. Cross-site request forgery will only be effective if a victim is authenticated. This means that the victim must be logged in for the attack to succeed. Since Csrf attacks are used to bypass the authentication process, there may be some elements that are not affected by these attacks even though they are not protected against them, such as publicly accessible content. For example, a public contact form on a website is safe from Csrf. Such HTML forms do not require the victim to have any privileges for form submission. Csrf only applies to situations where a victim is able to perform actions that are not accessible to everyone. A Csrf attack example using a GET request. HTTP GET is by its very nature meant to be an idempotent request method. This means that this HTTP method should not be used to perform state changes. Sending a GET request should never cause any data to change. However, some web apps still use GET instead of the more appropriate POST to perform state changes for operations such as changing a password or adding a user. When the victim clicks the link provided by the attacker using social engineering, the victim is directed to the attacker's malicious site. This website executes a script that triggers the user's web browser to send an unsolicited request. The victim is not aware that this unsolicited client-side request is being sent. However, server-side it appears as if the user sent the request because it includes cookies used to verify that the user is who they say they are. Let's imagine that www.example.com processes fund transfers using a GET request that includes two parameters, the amount that is to be transferred and the identifier of the person to receive the money transfer. The below example shows a legitimate URL, which will request that the web app transfers 100,000 units of the appropriate currency to Fred's account. The request includes a cookie that represents the authenticated user, so there is no need to define the source account for the transfer. If a normal user accesses this URL, they need to authenticate so that the application knows the account from which funds are to be withdrawn. Using Csrf, we can trick a victim into sending the request that the attacker wants while authenticated as the victim. If the exploited application expects a GET request, the attacker can include a malicious !img tag on their own website. Instead of linking to an image, this tag sends a request to the bank's web app. Under normal circumstances, the user's browser automatically sends cookies that are related to that website. This causes the victim to perform a state change on behalf of the attacker. In this case, the state change is a transfer of funds. Note that this example is very simple and it does not necessarily reflect the real world, but it shows very well how Csrf attacks work. However, similar vulnerabilities based on GET appeared in popular software in the past. Read more about it on Wikipedia.
Okay, so there are examples on Wikipedia here. Force a torrent file download, change uTorrent administrator password. So if the torrent was using these get methods, they could have done that.
Csrf attacks using post requests. Most state-changing requests are done using HTTP post requests. This means that web apps are more likely to accept POST instead of GET when a state change is involved. In the case of POST, the user's browser sends parameters and values in the request body and not the URL as in the case of a GET request. Tricking a victim into sending a POST request may be slightly more difficult. With a GET request, the attacker only needs the victim to send a URL with all the necessary information. In the case of POST, a request body must be appended to the request. However, an attacker can design a malicious website to include JavaScript that causes the user's browser to send an unsolicited POST request as soon as the page loads. The following JavaScript example shows the onload function, which automatically sends a request from the victim's browser as soon as the page loads.
Okay, let's check out the function. Document Csrf Csrf submit on load. Form action example com transfer method post name Csrf hidden type form. Okay.
As soon as the page loads, the JavaScript onload function ensures that the hidden form is submitted, which will in turn send the post request. The form includes two parameters and their values that have been set up by the attacker. The post target, example.com, identifies the request as legitimate because it includes the victim's cookies. An attacker can also make use of an iframe with attributes that make it invisible. Using the same onload function, the attacker can load the iframe containing a malicious web page and cause a request to be sent as soon as the iframe loads. Another option is to use XML HTTP request technology. Preventing Csrf vulnerabilities. Security experts propose many Csrf prevention mechanisms. This includes, for example, using a referrer header, using the HTTP-only flag, sending an X requested with custom header using jQuery, and more. Unfortunately, not all of them are effective in all scenarios. In some cases, they are ineffective, and in other cases, they are difficult to implement in a particular application or have side effects. The following implementations prove to be effective for a variety of web apps while still providing protection against Csrf attacks. For more advanced Csrf prevention options, see the Csrf prevention cheat sheet managed by OWASP.
Let's see that cheat sheet. Okay, always use same site cookie attribute for session cookies. Implement at least one mitigation from defense in depth mitigation session and other things. Oh, it is really long. Okay, so let's continue.
What are Csrf tokens? The most popular method to prevent cross-site request forgery is to use a challenge token that is associated with a particular user and that is sent as a hidden value in every state-changing form in the web app. This token, called an Anti-Csrf token, often abbreviated as Csrf token or a synchronizer token, works as follows. The web server generates a token and stores it. The token is statically set as a hidden field of the form. The form is submitted by the user. The token is included in the post request data. The application compares the token generated and stored by the application with the token sent in the request. If these tokens match, the request is valid. If these tokens do not match, the request is invalid and is rejected. This Csrf protection method is called the synchronizer token pattern. It protects the form against cross-site request forgery attacks because an attacker would also need to guess the token to successfully trick a victim into sending a valid request. The token should also be invalidated after some time and after the user logs out. Anti-Csrf tokens are often exposed via AJAX, sent as headers or request parameters with AJAX requests. For an anti-Csrf mechanism to be effective, it needs to be cryptographically secure. The token cannot be easily guessed, so it cannot be generated based on a predictable pattern. We also recommend to use anti-Csrf options in popular frameworks such as AngularJS and refrain from creating own mechanisms, if possible. This lets you avoid errors and makes the implementation quicker and easier.
Another method is same-site cookies.
Same-site cookies. Csrf attacks are only possible because cookies are always sent with any requests that are sent to a particular origin related to that cookie. See the definition of the same origin policy. You can set a flag for a cookie that turns it into a same-site cookie. A same-site cookie is a cookie that can only be sent if the request is being made from the origin related to the cookie, not cross-domain. The cookie and the request source are considered to have the same origin if the protocol, port, if applicable, and host, but not the IP address, are the same for both. A current limitation of same-site cookies is that unlike for example Chrome or Firefox, not all current browsers support them and older browsers do not work with web apps that use same-site cookies. Click here for a list of supported browsers. At the moment, same-site cookies are better suited as an additional defense layer due to this limitation. Therefore, you should only use them along with other Csrf protection mechanisms.
Okay, now we have an idea about what it is. Okay. How XSS works?
How cross-site scripting works. There are two stages to a typical XSS attack. To run malicious JavaScript code in a victim's browser, an attacker must first find a way to inject malicious code payload into a web page that the victim visits. After that, the victim must visit the web page with the malicious code. If the attack is directed at particular victims, the attacker can use social engineering and/or phishing to send a malicious URL to the victim. For step 1 to be possible, the vulnerable website needs to directly include user input in its pages. An attacker can then insert a malicious string that will be used within the web page and treated as source code by the victim's browser. There are also variants of XSS attacks where the attacker lures the user to visit a URL using social engineering and the payload is part of the link that the user clicks. The following is a snippet of server-side pseudocode that is used to display the most recent comment on a web page.
Okay, so you see they directly print the comment into the page without any encoding, and if there is no encoding, then it will be treated as a HTML code or JavaScript code, whatever it is. Therefore, it will be directly executed and not as a command but as a HTML or source code.
The above script simply takes the latest comment from a database and includes it in an HTML page. It assumes that the comment printed out consists of only text and contains no HTML tags or other code. It is vulnerable to XSS because an attacker could submit a comment that contains a malicious payload, for example,
like do something evil script. Okay.
When the page loads in the victim's browser, the attacker's malicious script executes. Most often, the victim does not realize it and is unable to prevent such an attack. Stealing cookies using XSS. Criminals often use XSS to steal cookies. This allows them to impersonate the victim. The attacker can send the cookie to their own server in many ways. One of them is to execute the following client-side script in the victim's browser. The figure below illustrates a step-by-step walkthrough of a simple XSS attack.
Okay, you see at the first step, the attacker posts a command that includes the malicious script. At the second step, the victim visits the command posted page, and at the third step, the page the victim visiting displays the command without any sanitization or encoding, and therefore after the page loads on the victim's browser, the malicious code of the attacker executes, and whatever it is doing, it is being made here. Okay, and okay, let's see. You see all of these tags are used for XSS attacks, script tag, and body tag with onload on error, image tag, iframe tag, input tag, and link tab, table tag. You see like this, and div tag, object tag. Almost any of them are any of the HTML tags are vulnerable. Okay, this was about cross-site scripting. Now email header injection. I will take a pause here. All right. What are email injection attacks?
It is common practice for web pages and web applications to implement contact forms, which in turn send email messages to the intended recipients. Most of the time, such contact forms set headers. These headers are interpreted by the email library on the web server and turned into resulting SMTP commands, which are then processed by the SMTP server. Unfortunately, user input is often not validated before being sent to the email library. In such cases, the contact form might be vulnerable to email header injection, also referred to as SMTP header injection or simply email injection. A malicious user may be able to introduce additional headers into the message, thereby instructing the mail server to behave differently than intended. Email injection is not directly dangerous to the owner of the web server, but a vulnerable contact form may be used for sending spam or for phishing. This makes it a serious application security vulnerability. How SMTP works. The SMTP protocol, Simple Mail Transfer Protocol, is one of the oldest protocols of the Internet. Originally, it just accepted a small set of commands that simply stated who the email sender is and who the recipient is. With time, email became much more complex, and email headers were added. To understand how SMTP works, you need to first understand the difference between the envelope and the email body. The envelope is the initial part of the communication and it is part of the actual SMTP protocol. The following commands are part of the envelope.
Okay, so what parts it has? Mail from. Okay, let's read them.
Mail from, this command sets the envelope sender. RCPT to, this command sets the envelope recipient. It can be used multiple times if you want the message to reach many people at once. Data, this command begins the email payload. The payload contains email headers and the message body separated by a single empty line. The email headers are not part of the SMTP protocol. They are interpreted by the mail client to display the email correctly, but also by some email handling libraries in programming languages. Here are some examples of such headers. From, this header sets the visible sender and it can be different than mail from content. In most email clients, the sender provided using mail from is visible in the return path header that is hidden by default. 2. This header sets the visible recipient and it can be different than RCPT to content. In most email clients, the recipient provided using RCPT to is visible in the delivered to header that is hidden by default. Here is an example of a simple SMTP dialog.
Okay, let's analyze the dialog. So there is mail from and recipient to, sent message content, content type, date, from, to, and such.
The above email would be received by Anna at example.com and Barbara at example.com. However, they would see that it was sent by Santa Claus at acunetics.com, not Postmaster at acunetics.com, and they would see that the recipient is not Naughty at example.com. Most email libraries in web programming languages usually do not let you add envelope commands directly. However, they take the email headers that you supply and often convert them into equivalent SMTP commands. For example, if you add a BCC header, the email library may take the content of that header and create additional RCPT to commands. With such libraries, all that the attacker needs to do is to know how to add email headers and they will be converted into equivalent SMTP commands.
Okay, let's see the vulnerable code.
Vulnerable code. The following PHP code is an example of a typical contact form that is vulnerable to email header injection. It takes the name and email address from the input fields and prepares a list of headers for the email.
Okay, a type.
A typical genuine post request would be as follows.
You see name, reply to, and message. An attacker, let's see.
An attacker could abuse this contact form by sending the following post request. The attacker inserts a new line, align feed n on most Unix and Linux systems, and a carriage return and align feed r n on Windows systems, and appends a BCC header that containing additional email addresses. The email library converts these addresses into RCPT to commands and delivers the email to them in addition to the intended recipient. The attacker could use such tactics to send large numbers of messages anonymously. They may also send phishing emails where the recipient believes that these messages are originating from a trusted source.
You see, they could abuse your system to send their spam email to unrelated people. If you don't take the necessary precautions, and therefore the reliability and credibility of your email server would get a lot of harm and damage from sending spam emails without even you are being aware of it.
While this vulnerability is not limited to the PHP mail command, some email libraries are naturally resistant to it. For example, the SMTP-lib in Python is resistant because SMTP, sendmail, needs you to specify an explicit list of recipients. If the attacker adds headers, it will only change the way that the email appears.
Okay.
Detecting email header injection vulnerabilities. In order to detect email header injections automatically, the vulnerability scanner needs an intermediary service. The detection of such vulnerabilities requires out-of-band and time delay vectors. Acunetics solves this by using the Acu monitor as its intermediary service. During a scan,
and there is mitigation.
Mitigating against email header injection involves validating user input. You must not allow any newline characters in the input because they let the attacker append email headers. In general, when validating user input, the simplest and most robust way to achieve strong input validation is through a whitelist of allowed characters.
Whitelist is the greatest solution in many cases. So you only allow certain input to be used. Therefore, they cannot possibly use any combination, any vulnerability, any exploit to bypass your security. So whitelist is the best way. If you use a block list, it is much harder because it is very hard to prevent malicious every kind of input. So there could be hundreds, thousands of different inputs that can cause harm, and it is hard to block all of them. Instead, you just allow certain input to be entered, therefore you are being sure. This is whitelist method. Okay, host header injection.
What is a host header attack? It is common practice for the same web server to host several websites or web applications on the same IP address. This is why the host header exists. The host header specifies which website or web application should process an incoming HTTP request. The web server uses the value of this header to dispatch the request to the specified website or web application. Each web application hosted on the same IP address is commonly referred to as a virtual host. So what constitutes a host header attack? What happens if we specify an invalid host header? Most web servers are configured to pass the unrecognized host header to the first virtual host in the list. Therefore, it's possible to send requests with arbitrary host headers to the first virtual host. Another way to pass arbitrary host headers is to use the X-forwarded host header. In some configurations, this header will rewrite the value of the host header. Therefore, it's possible to make the following request: get HTTP 1.1.
Host example.com and X forwarded host is www.attacker.com.
Many web applications rely on the HTTP host header to understand where they are. Unfortunately, what many application developers do not realize is that the HTTP host header is controlled by the user. As you might already know, in application security, user input should always be considered unsafe and therefore never trusted without properly validating it first. The use of the host header is especially common in PHP web applications, however, it's certainly not a problem endemic to PHP web applications. The PHP script in the following example is a typical and dangerous use of the host header. An attacker can potentially manipulate the code above to produce the following HTML output just by manipulating the host header. The two major attack vectors host header attacks enable are web cache poisoning and abuses of alternative channels for conducting sensitive operations, such as password resets. Web cache poisoning. Web cache poisoning is a technique used by an attacker to manipulate a web cache to serve poisoned content to anyone who requests pages. For this to occur, an attacker would need to poison a caching proxy run by the site itself, or downstream providers, content delivery networks (CDNs), syndicators or other caching mechanisms in between the client and the server. The cache will then serve the poisoned content to anyone who requests it, with the victim having no control whatsoever on the malicious content being served to them. The below is an example of how an attacker could potentially exploit a host header attack by poisoning a web cache.
So this attack can be successful only if you are connecting to a, let's say, a web cache such as content provider, CDN, content delivery network or such. So you see, you are trying to connect example.com and then the host returns to attacker.com. Therefore, you are getting redirected to there.
Password reset poisoning. A common way to implement password reset functionality is to generate a secret token and send an email with a link containing this token. What could happen if an attacker requests a password reset with an attacker-controlled host header? If the web application makes use of the host header value when composing the reset link, an attacker can poison the password reset link that is sent to a victim. If the victim clicks on the poisoned reset link in the email, the attacker will obtain the password reset token and can go ahead and reset the victim's password. Detecting password reset poisoning vulnerabilities. We'll use an old version of Piwik, an open-source web analytics platform, which was vulnerable to password reset poisoning via a host header attack for demonstration of this vulnerability. In order to detect password reset poisoning automatically, we'll need to rely on an intermediary service since the detection of password reset poisoning via a host header attack requires an out-of-band and time delay vector. Acunetics solves this by making use of AcuMonitor as
Okay. I would say that this is extremely rare case to be happen. Okay, we get the idea. So let's see LDAP injection.
LDAP injection. Description: this script is possibly vulnerable to LDAP injection attacks. Lightweight Directory Access Protocol (LDAP) is an open standard protocol for both querying and manipulating by.500 directory services. When a web application fails to properly sanitize user-supplied input, it is possible for an attacker to alter the construction of an LDAP statement.
Yeah, this looks like an extremely rare case. And OS command injection.
What is OS command injection? OS command injection, operating system command injection, or simply command injection, is a type of an injection vulnerability. The payload injected by the attacker is executed as operating system commands. OS command injection attacks are possible only if the web application code includes operating system calls and user input is used in the call. They are not language specific. Command injection vulnerabilities may appear in all languages that let you call a system shell command: C, Java, PHP, Perl, Ruby, Python, and more. The operating system executes the injected arbitrary commands with the privileges of the web server. Therefore, command injection vulnerabilities on their own do not lead to full system compromise. However, attackers may be able to use privilege escalation and other vulnerabilities to gain more access. Note: command injection is often confused with code injection. Code injection vulnerabilities let the attacker inject code in the programming language in which the web application is built. Command injection example. The developer of the example PHP application wants the user to be able to see the output of the Windows ping command in the web application. The user needs to input the IP address and the application sends ICMP pings to that address. Unfortunately, the developer trusts the user too much and does not perform input validation. The IP address is passed using the get method and then used in the command line.
So you see the developer here directly executing the commands as this, which takes the IP address, and therefore the abuser can do anything with this shell execution command, and such as you see it uses this instead of an IP address. Let's see what happens.
The shell_exec function executes the following OS command: ping n38.8.8.8 and dir. The n symbol in Windows separates OS commands. As a result, the vulnerable application executes an additional command dir and displays the command output directory listing on screen.
So they can get the directory listing on screen with this. So this ends the shell command, and the other part of the entire command is being executed as another standalone command. You understand the attack style?
Command injection special characters. You can use different special characters to inject an arbitrary command. The The simplest and most common one for Linux is the semicolon, winking face, and for Windows, the ampersand, and. However, the following payloads for the ping.php script will also work.
So you see there are some special commands. To prevent this, you need to validate the input or sanitize it by removing the non-allowed characters from the input, and it is up to you how you solve the problem. It is so easy. Just sanitize or verify the input. Okay, and then SQL injection, we have already seen it. And then XPath injection.
XPath injection vulnerability. Description: this script is possibly vulnerable to XPath injection attacks. XPath injection is an attack technique used to exploit websites that construct XPath queries from user-supplied input.
Okay, one moment. So,
Applications that use XML databases are vulnerable to injection attacks. Read on to find out how XPATH queries are manipulated to access sensitive information in a typical web application architecture. All data is stored on a database server. This server can be storing data in various formats like an RDBMS database, LDAP, or XML. Based on the user input, the application queries the server and accesses the information. Attackers manage to extract more information than allowed by manipulating the query with specially crafted inputs. Here, we'll be discussing XPATH injection techniques to extract data from XML databases. Before we go deeper into understanding XPATH injection, let's take a brief look at what XML is and how an XPath query is formed.
Okay, let's see. So you execute XPath to get some data, like here, and if you don't validate the input, there will be XPath vulnerability. Okay, this is a very rare case. If you are using such thing, be aware of it. Okay, this is all, and this was our latest lecture of this course. Hopefully see you later in the future courses. End of lecture 14. Do not take the semester project lightly. Please work on it and give it your best. Try to make your best report. End of lecture.